see where we were last time we met. So the branches used expressions yield, so I guess we're continuing with the yield statement. I just tried to build the docs from this branch and I got an error because yield from is not a single keyword. I think this will fix it. And where were we?
Oh, did we start the recording?
Yeah, I already started it.
Okay.
So yield expressions. This is the one. So it goes through generator functions. Then we have value, yield without a value, value of the yield expression. Then there's throwing exceptions into generators, which we don't have yet. Parentheses around yield expressions. Yield expressions and try. And then yield from expressions. Oh, we had this silly example with the dancing, which doesn't really scale too much. I wonder if there's a better example in the PEP, like PEP 380 syntax for delegating to a subgenerator. Did we already look here?
I don't think so. This doesn't.
Examples and implementation. Right. Yield from and co-functions. Okay, simple examples. Binary tree. Binary tree that produces an in-order traversal of its items when iterated over, courtesy of Scott Dial. So, copyright is murky, I guess, unfortunately. But yeah, this.
Oh,
okay.
Yeah,
go ahead.
Is it copyrighted?
Well, everything's copyrighted.
It
doesn't say what the license is.
Right, okay. Alright.
Probably can't use it. So there's a binary tree. Left, us, and right. What is us? I don't know.
Left, us.
Oh, I guess us is the value of the tree node. Okay, so it yields from self left, then it yields the value, and then it yields from self right. Yeah. Okay, so this is so simple, it's probably not copyrightable. For comparison, here's the same thing using for loops, which instead of yield from, it just uses for. So this is a neat example for readers who already know about binary trees.
Yeah, exactly.
Then we have co-functions. And I guess this became async def later. So there's a parser example and there's a scheduler example. Did I click the parser discussion? Okay, so this is two complex for a docs example. A scheduler, I guess, as well. And this doesn't use the return value of the yield from, which is the example we have trouble with. Okay, so now a good example here. I'll just keep the current example and go on. Maybe we'll find something better afterwards. So yield from expressions. Maybe we should not do this example at all. Just remove it. Like this continues with the dancing, but it's somewhat arbitrary. Don't like this example at all, so I'll remove it for now. It says any values passed in with send and any exceptions passed in with thrown, maybe not passed, but throw are passed to the underlying iterator if it has the appropriate methods. If this is not the case, the send will raise attribute error or type error, while throw will raise the passed in exception immediately. Passed is probably the best word to use here. Right, and then we have the original text, so let's see if we covered it all. So the yield expression can only be used in the body of a function definition. Do we have that somewhere? Don't, do we? should be right at the start. Precisely, it can only be used when the closest enclosing block is a function definition, not a module level class block. So where do we want to say this?
How do you mean? Where can we what? Save it?
Where do we say that the yield expression can only be used in the body of a function definition?
Oh. Well, where else would one use it? Oh, I see. It has to be. Oh, yeah. You can't just like one off in like.
Yeah. I guess this is similar to the return statement. Maybe we can just link to there. And the return statement would be not in expressions but in simple statements, which is coming up next. So return may only occur syntactically nested in a function definition, not within a nested class definition, which is a very simple way to say it.
So we would say the same thing about yield functions, yield expressions.
I would just link to there.
Oh, okay.
So I'll add this to my notes for when we get to the return statement. But for the yield expression, we can say this. Expression may only occur syntactically nested in a function definition, not on the module level or within a nested class definition. This restriction is similar to let's say the return statement, which similar to the return statement, the yield expression may only occur syntactically nested in a function definition, not on module level, nor within a nested class definition, or maybe not within a nested class definition. Using a yield expression causes the enclosing function to be a generator function. Each yield expression denotes a suspension point, blah blah blah. And we go on. So that would be it for this part. And the example, I think, is better, or will be better in the return statement, which many people are familiar with, and there's also more space to explain this. Right, and then we have, due to their side effects on the containing scope, yield expressions are not permitted as part of the implicitly nested scopes used to implement comprehensions and generator expressions. Where do we put this? Or should we add a special section explaining the limitations?
We have that section, the section 288, which just says examples. Maybe we should clarify that, like
oh yeah, that's the part we haven't gotten to yet. Like there's generator, iterator methods, and on.
Oh, I see.
That's the original stuff that we didn't get to yet. But maybe after the yield from expressions, there should be a section on the details and maybe we want to put the whole thing here. Maybe not call it limitations, but where yield expressions can occur. It's like the constraints on where you can put them.
I see. So it's more like the requirements or the conditions.
Where yield expressions are allowed. That's what I would want to say, but in a more technical wording.
Placement, position.
Yeah, limitations on placement.
Okay.
Yeah, something like that. Would that be better? Yeah. It's longer. It doesn't really help. Okay, but if we do add this here, then we can link to there instead of the return statement. then we have the formal grammar. And then we can sort out these version changes. So yield expressions prohibited. That would be here. The parentheses may be omitted when the yield expression is the sole expression on the right hand side of an assignment statement. We have that covered. Up above, you added yield from expert, so that should be there. Index single coroutine. So I guess those index entries should be for the whole yield expression. Oh no, that should be for the yield from. Or maybe coroutine could be. Where does, like, how do we document coroutine now? Types coroutine. Transformers generator into a coroutine function. Coroutine function may be defined with the async def statement. Okay. So coroutines are now something entirely different, and we should remove this index entry from yield, because now we have async def. We have simple generators, coroutines via enhanced generators. What did pep342 do? So yield is allowed inside try finally, there's a throw, there's a generator exit, and there's a close. And there's a send. Alright. So simple generators would be would go here. Then coroutines via enhanced generators. That would go, I guess, into value of the yield expression. Then there's syntax for delegating to a subgenerator, which is yield from. And then there's the pep for asynchronous generators, which comes after the examples here. Because first we have this generator iterator methods. Which should probably go on its own page. Then there's an example here. Maybe this one will be useful. So what does this do? Echo. Execution starts when next is called for the first time. Then it does try while true value is yield value. E, and don't forget to clean up when close is called. Okay, so this example would be for here, value of the yield expression and throwing exceptions into generators. For examples, using yield from, see PEP 380, which doesn't really have any examples, except an additional material. And, oh, and what's new in Python? Ah. Okay. Oh, this is some good wording. Maybe we should steal this wording for.
I think so. Yeah.
For what? For yield from expressions. Yeah, let's just steal this. So where's this? What's new in what's new 3.3? Okay. Yield from expressions. All right. Okay. So when yield from expresses the supplied expression expression must be iterable. We can use this samp thing here. So the expression must be iterable. The values produced by that iterable are passed directly to the consumer of the current generator. Maybe we can say instead of producing a single value, like yield expression, a yield from will delegate delegate to the given generator. One of those two. Okay, this says right. So yield from is for delegating to another generator. But while designed primarily for that, it actually allows delegation to arbitrary sub-iterators.
Oh, sub-iterators. That's a clever way of saying it.
Right. Oh, and maybe we can start with a simple case. I like doing that, right? For simple iterators, yield from iterable is essentially a shortened form of for item in iterable.
Okay.
Yield item. Nice. Simple case first. Okay. However, unlike an ordinary loop, yield from allows sub-generators to receive set and thrown values directly from the calling scope and return a final value to the outer generator. Let's do this. So this is an example from what's new. So what does this do? Accumulate. Oh, this is the running something. Tally 0 while 1. Whoa. Next equals yield. If next is none, then return tally. Tally plus equals next. So this is a normal generator, and I don't know if we have covered return here. Yes, we have. I think we should probably cover yield expressions from the coroutine stuff somehow. Okay, so if next is none, then we return tally, otherwise we increase the tally. Then we gather tallies. We yield from accumulate and append tally. So tallies is a list. We call gather tallies on it. We start the generator, then we send 4 numbers to it, then send a none, which generates a tally. Then we send 5 numbers to it, send a none to it, one which finishes as tally again, and then we get tallies with the sum of the first 4 numbers, which is 0, 1, 2, 3, 6, and then the first 5 numbers, which is 1, 2, 3, 4, 5, 1, 2, 3, 4, and we get 10. This doesn't look like a good example to me. Right?
Yeah, it's a little.
Like if your problem was gathering tallies from a list from sequences of numbers, there are much better ways to write that. Which I guess this is the whole problem with like next and throw on generators, because all of the use cases have now moved to async functions. Or almost all of the use cases.
I'm sorry. From what kind of functions?
Like the use cases for yield getting values from yield statements, and which means sending values using the send method of generators and throwing exceptions into generators. Most of those use cases have moved to asynchronous functions.
Yes.
So it's really hard to come up with a good example. But maybe asynchronous functions themselves have some good examples. Let's see. So that would be compound statements, function definitions, coroutines, coroutine function definition, async funcdef. Execution of Python coroutines can be suspended. Okay.
Oh, async for and async with. Interesting. But there's no async from.
Async from.
Yeah, I guess that's that's probably what a yield from would be. I just noticed that there was an async for.
Oh, that's await.
And an async with. Oh, await. Oh, okay.
So basically, async functions are like generators, but they don't use yield. They always use yield from.
I see. Okay.
And they spell it await. Async for, async with. Yeah, this is very simple. And I think we have too much in here. So maybe get rid of this example. Okay, this is talking about the change. Okay, so the values produced by that variable are passed directly to the consumer of the current generator. However, unlike another loop, blah blah blah. Okay. So there's devgx. This is probably a better example than the gx. It's at least fun. When the underlying iterator is complete, the stop iteration value attribute of the raised stop iteration instance becomes the value of the yield from expression. It can be either set explicitly when raising stop iteration or automatically when the stop iterator is generator. Blah blah. Any values passed with send through are passed to the underlying iterator. So as I think about this, because this is really unwieldy, so maybe what I want to do is explain simple generator functions, and they then say something like to support yield-based coroutines. You can also use yield. You can also like the yield expression also has a value, and you can use yield from. And then basically give the grammar and say look at the description of generator, generator iterator objects or generator iterator function. at the description of generator iterators to see how this all works. And then have this generator iterator object on some different page. I don't know if that would be in the language reference. And there's the data model, which has standard type hierarchy. It's a very flat hierarchy, which includes slice objects, static method objects, frame objects, internal types. And I guess generator iterators would or should be mentioned here. So what do we have here? Internal types. Few types are used internally by the interpreter as exposed to the user. Their definitions may change with future versions of the interpreter. They are mentioned here for completeness. So this is definitely true for code objects. Right, so I wonder if function objects are... Oh, there are user-defined functions created by function definition. And you have the code object for the function. And the code objects are internal. Okay. Then yeah, frame objects, which are definitely CPython specific. So I would guess that's what internal means. So some Python implementations don't have frame objects, and they definitely don't need to have all of these attributes. Traceback objects, okay, those are internal. But then slice objects, well, we definitely cannot change the definition of slice objects. So these should probably be moved out of this section. We have static method objects and class method objects. Okay, so these belong here. There's callable types, user-defined functions, instance methods, generator functions, coroutine functions, asynchronous generator functions, and built-in functions built in methods, classes, and class instances. Instances which are also in a separate section. Why? Class instances are just objects. Custom classes. What about built-in classes? maybe you remember me saying this. This page needs an overhaul as well. Right now I want to put generator iterators somewhere in there.
Okay.
And then we have asynchronous generator iterator methods.
I'll just put a little note here that that's what we're doing.
Asynchronous generator functions. Generator iterator methods, asynchronous generator iterator methods. Do we have any docs in the data model on iterators? Iterator types. Oh no, that's an std types. So there's iterator types and generator types. Generators provide blah blah blah. More information about generators can be found in the documentation of the yield expression. Maybe we should move that here. Okay, so this wants to. This makes me want to abandon. Pause the work I'm doing right now on the yield expressions, and first send a pull request to move this generator iterator methods section somewhere else. There are two other places to put it. There's generator types and built-in types, and then there's generator functions and the data model. Generator functions is in callable types. And that should probably there should probably be a new section somewhere here for generators or generator iterators. Oh, there's already coroutines, awaitable objects, coroutine objects, asynchronous iterators. Oh, why is coroutines its own section, and it's not part of the standard type hierarchy. Okay, so that's what I'm doing. I'm doing a new branch. Move generator iterator out. Alright. So this is a new branch. I've based it on the current main. And the goal here will be moving generator iterator methods and asynchronous generator iterator methods out of here and into, I think, into data model, which has a lot of this kind of reference material for the built-in objects. Does that make sense? Hope it does.
Yeah, it sounds good. It does.
Okay, so generator iterator methods. Take that and figure out a place to put it in the data model. So standard type hierarchy, blah 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 blah, callable types, modules, custom classes, class instances, IO objects, internal types, that's the names and coroutines. Callable types and then modules. Custom classes, class instances, IO objects, internal types. So let's just put it after IO objects, I don't know. Data model, right? So we have iterators. And then instead of list of methods, this should be the documentation of generator iterators. Right? And the same with asynchronous generator iterators.
Yeah, that's a lot more consistent.
I'm just worried that people will, like the reviewers will see the inconsistencies in the data model chapter and want me to refactor more of that than I'm ready for. This should really be split up in so many ways. Anyway, we probably need to document something about iterators, and that should probably come from here. Alright, there's built-in types, there's iterator types, there's generator types. Like, why is data model and built-in type? They like data model has what mappings, and built-in types has mapping types, dict and frozen dict. Should this be here? Ah, that should be here, not there. So std types in where? In library. Next to generator types. Okay, Python's generators. Let's just link the whole thing. Provide a convenient way to implement the iterator protocol. If a container object's iter method is implemented as a generator, it will automatically return an iterator object, technically a generator object, supplying the iter and next methods. What? What? This is about built-in types, right? Where did I see the...
Yeah.
now you say if a container objects, like if you define your own custom type. Yeah, I guess this is a consequence of these pages being so long, you can't even see what the whole page is about when you edit it. Like, should the information be here or there? Should we start adding new pages that consolidate this and that?
Like a whole new page, I suppose.
No, because you have ellipses in the data model.
Yeah.
Like, objects are
Fair
Python's abstraction of data. Standard type hierarchy. Below is a list of the types that are built into Python. You can define more. Ellipses. Blah, blah, blah. And then you have the built-in types. The following sections describe the standard types that are built into the interpreter. There's a bunch of them. They're different. And do you have ellipses here? Yeah, other built-in types. The interpreter supports several other kinds of objects. Blah, blah, blah. Ellipses. More info about ellipses. Like, what's the difference between this ellipsis and that ellipsis? Like,
Is there a difference?
no.
Oh, dot.
I mean, there's a lot more information here, but the same information could be here.
The ellipsis object appears in a few different places. Type annotations, okay. Body of a function. But that doesn't sound very helpful.
Yeah. We have modules. The only special operation on module is attribute access and .name. Where M is a module and name access is blah blah blah. A special attribute of every module is standard dict, so that's the other special operation. And if you go to data model and you look at well, that's not internal here. It's here. There's like sections of special operations on modules. So maybe I put it in one of the two places and link from the other one. So I chose std types right now. Let's see how that looks. Built-in types. So iterator types, right? This has some methods from it, right? It supports the concept of iteration over containers. This is blah blah blah. Sequences always support the iteration. Sure. One method needs to be defined on container objects to provide iterable support. Right. iterator objects themselves are required to support the following two methods. Okay, maybe let's put sections on that. XXX duplicated and reference data model. Yeah, somebody realized that. Do we remove that? Does this duplicate the next method? No. Good. Okay. Good. Okay, so let's not call this iterator types if this talks about iterable types. What's the context here? Sequence types, numeric types. Iteration related types will be iterators, or iterables, right? Okay, we could talk more about when you would have an iterable and when you have an iterator. But that's probably out of scope for now. So the iterator objects themselves are required to support the following two methods, which together form the iterator protocol. Iter and next. So iterator returns the iterator object itself. So allow both containers and iterators to be used, blah blah blah. I would rather say iterables. Or containers. I don't know, is range and a container? Probably. Is a generator a container?
We have is a generator container? I suppose it is.
Well, it's not. Yeah. Container. I would hope we have a glossary entry for container. Do we? No, we don't. Okay.
Uh-oh. Okay. We probably ought to. Because honestly, I think I thought of a container as something a little bit differently. Okay. Name type. Oh, they're listed right there.
General purpose built-in containers are text lists and a tuple. How about maybe it's fine that container is like a generic term. but it seems in this case we define containers as iterators, or well, as iterables except iterators. Like the iterables that are not already iterators are containers, or something like that, formally. Well, I guess it's fine to use the term here. So this is required to allow both containers and iterators to be used with for and end statements. This method corresponds to the TP-iter slot of the type structure. Whoa, that's deep. So next, return the next item from the iterator. If there are no further items, raise the stop iterator exception. This method corresponds to the TP-iter next slot. Okay. Python defines several iterator objects to support iteration over general blah 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 blah. The specific types are not important beyond their implementation of the iterator protocol. Okay. Once an iterator's next method raises stop iteration, it must continue to do so on all subsequent calls. Implementations that do not obey this property are deemed broken. Great. Okay, so that's wait. So that's iterables, iterators, and then we have generator types, which we're adding, and we need to make them fit in. Python's generators provide a convenient way to implement the iterator protocol. If a container object's iter method is implemented as a generator, it will automatically return iterator objects. Generator iterator object supplying this. Okay, and what does the term generator link to in here? That's formally not well defined. Okay, let's define it formally. Like, what do we do here? We make an example. Def, I don't know. Count to 3. And we yield the numbers up to 3. And then we do our number and count to 3. Go, and then we get the numbers, right? Some simple example like that. this the place to add detail about the usage? A function that contains the yield expression. Here we look back to the syntax thing. Where is it? Yield expression. Function that contains one or more yield expressions is can generate a function. For example, calling this function returns generator iterator. For example, if we call this function, and I should probably try that. I get a generator object. Okay. And the function itself is just a normal function. Functions behave as normal functions, which we probably have somewhere. Yeah, here. Functions. Of operations and attributes, which we should probably link to the definition here. User-defined functions. This one. So this is how do we link to this in the data model? User-defined functions. Behave is probably not the right word, right? And these these just have attributes, not much of methods. So what would be a good user-defined class? That would be an iterator. I guess after 2 hours I'm out of ideas.
Oh, I should just making a note of that. Are we on built-in methods? Standard types. Okay.
So if a container object's iter method function. Okay, let's make this about usage. The iter method of custom objects may be implemented as a generating function. Will return this.
Yeah.
Like this. All right. But this is not really about generator types. So maybe let's cut this.
Okay.
Like this.
Oh, I see. Nice. Okay, fine. Good.
And now we say generator iterators. Or maybe let's say generator iterators have a few few more functions, and then generate iterators. And since we are documented next, then we should probably do this one. Something like this. Which brings us to the end of this session,
Yeah.
because we're out of time.
Yeah, good. Good, very nice.
So I'll push this to my repository if anybody wants to take a look at it. It's work in progress, of course. And
Yeah.
we'll continue next time. So next week, I'll be here. Your
Okay,
Python
cool.
is a week
That
after
sounds
that,
great.
so next week's fine.
Yeah.
Right.
Fabulous.
Thanks for your attention, and